In describing the search for a theory of everything in physics, you describe the history of physics can be told effectively as a kind of history of unifications. There's this centuries-long quest to show that these distinct phenomena are actually linked by some unified underlying principles, even starting with Newton, that you can think of the effort of physics as one as trying to unify the laws of nature. So I was wondering if we could talk through the history of unification,
Sure.
that lens of physics.
There are, of course, lots of different ways to do physics, but the way that I would say that particle physicists, cosmologists do is they are trying to really find basically the underlying principles that govern the laws of nature. If we go back, say, to the, I don't know, 1650s or so, you're the most brilliant person around, and you've noticed two things. One you've noticed is that when you trip, you fall. That is the nature of gravity that we all experience day to day. But then there's sort of astronomy where you look out at the heavens and you see the stars march across the sky. You see the planets move through the stars. And that seems to have absolutely nothing to do with what happens when you drop your sandwich and the dog grabs it from you. So
Yeah.
the brilliant thing was when Newton looked at that and he thought about maybe the moon is falling, but it's missing the Earth. So what we had is that in maybe 1650, you had what we might call the laws of celestial gravity, the gravity that governs the heavens, and terrestrial gravity, the gravity that is here on Earth. Now, we don't think of it that way anymore. We think of it as just gravity. But at that time, that wasn't at all obvious. And in fact, if you look in the books, Newton's theory is Newton's law of universal gravity. The universal is there. And the reason is because he realized these two things that seemed to have nothing to do with one another were indeed one and the same. I mean, this is absolutely brilliant. I mean, Newton is arguably one of the most brilliant humans of which I'm ever aware. But at any rate, it is the first sort of easily to describe unification of physics that you can state in a way that sort of makes sense to modern humans. I mean, you can go back farther than that, where people are talking about chemistry, the nature of atoms. You go back to Democritus, who was wrong about very many things, but the idea that there was a smallest particulate form of matter is right. So it's kind of funny. You read the chemistry books, and they say that the idea of atoms goes back to Democritus, and his idea was that there was a smallest atom of oil, which was smooth. And it was smooth, of course, because, well, oil is smooth. There was a smallest atom of vinegar because vinegar is tart and it pricks your tongue. So therefore, atoms were little sharp, pointy things. And so he was wrong about a lot, but he was right about the idea that there was a small particle. And we now know we have a very different concept than he did. So you can go back farther than that. But getting to unification, there are more examples. For instance, if you go back to, say, 1830 or so, scientists were trying to understand electricity, for instance. And there was a lot going on. People really understood things. But at the time, you would have two phenomena that are familiar to us now. One is a magnet, which, at the time, mostly magnets were simply little pieces of iron that had been magnetized and they could stick to steel. And then you had electricity, which was, at the time, they were generating little sparks that they could play and have fun with, or more broadly, a lightning bolt blazoned across the sky. And so when you think about this, that lightning bolt and that little magnet seem to be really unrelated. But over the 1800s, a number of scientists were exploring little aspects of it. What happens when you run electricity through a wire? It seems to make a magnetic field. There was a whole bunch of experiments, and there were a lot of names. But in about the 1860s or so, James Clerk Maxwell took all of those ideas that had been percolating around for the previous 50 years and wrote his laws of electromagnetism. And they're really fascinating. If you look at the laws of electromagnetism, they're differential equations or integral equations. But basically, what they say is on one side, you have a bunch of terms that have electricity in them, and then you have equals on the other side a magnetism thing.
Hmm.
So forgetting all of the mathematical symbols, you have electricity side equals a magnetism side. Electricity equals magnetism. And that is a staggering concept. The fact that these two things, a lightning bolt and the magnet that holds your kid's art to the refrigerator, are one and the same. And this was another case where electricity and magnetism became unified into electromagnetism. So now we have two examples. One, gravity being unified, terrestrial and celestial gravity, and then electricity and magnetism. So I'll tell you about some more in a moment, but one thing that's kind of important, because the goal is, of course, to unify everything. That if I could do what I want to do, I would have some unified theory that would explain all the behavior of all energy, matter, space, and time, which is a grand goal.
And we should say that maybe one of the goals of science more broadly, outside of physics even, is to construct models that can generalize the world. So if you look at Darwinian evolution, that
Hmm.
was a very beautiful theory that captures another layer of reality of like how this particular thing that we see here on Earth happens.
Right.
So when we talk about theory of everything in physics, that's capturing a different layer of abstraction about the functioning of the universe.
Right. The whole Darwinian evolution, the fact that our genetics has significant overlap with the genetics of a banana is pretty staggering, is
Yeah.
astonishing that that works. So that is amazing. But for at least the class of scientists that I am, what we think of is, well, sure, biology is interesting and all, but when you get right down to it, it's caused, whatever happens in biology is caused by the movement of molecules. And then you say, well, that's great and all, but molecules, they do what they do because they're made of atoms.
Hmm.
And then the next step is, well, atoms, that's great, but atoms work the way they do because of the nucleus and the electrons. And then the nucleus is protons and neutrons. And so there are those of us, myself included, who want to dig down to the very, very bottom and find out what is the smallest building block of nature from which all of these other far more complex and interesting and abstract things are. But what is at the very, very bottom? And also, that's great. But if you know what the smallest building blocks are, that doesn't tell you the story. It's like having a whole bunch of Legos, but not knowing how to put them together. You also need to know how they interact, how they work. And so that's what we study forces. So there are the various subatomic forces of which we're familiar. And for instance, electricity and magnetism are components of electromagnetism, which then governs the behavior of things like this is amazing. Electromagnetism explains, of course, electricity, magnetism, but it explains how light works. It explains how much of chemistry works. So electromagnetism, 1860 or 70, the wonderful thing about that is if you take Maxwell's equations and you apply a little bit of calculus, it's very easy to see that the laws of electricity and the laws of magnetism combined together make what's called a wave equation, which that shows that these electric and magnetic fields oscillate, they vary. And if you have something that's varied, that's a wave, and the wave then moves. And if you do the math, you find out that the speed at which these waves move is the speed of light. And so people said, wow, the speed of light comes out of those equations. And that had to be, I think, very persuasive. And of course, electromagnetism also plays a really significant role in chemistry because, after all, atoms are held together by electromagnetic forces. There's more to how atoms work. There is all the quantum mechanics stuff. But if you did not have electromagnetism, or if electromagnetism was very different, then atoms would be very different. So it plays a very big role in holding us together.
Mm.
So it's a staggering advance in science to have a good behavior on that. And of course, being able to tame electromagnetism is why people can hear you when you do your podcast, because through the miracles of the internet, just electricity running the computers. I mean, this is a case, if I can get on a small soapbox, where people back then said, well, why are you messing around with magnets and sparks and who cares? Well, that very fundamental digging into the laws of nature has spin-offs, and it has spin-offs. One of the big spin-offs is our entire technological society.
Mhm.
Without being able to govern electricity, we'd still be farmers and shoemakers in cities, but we certainly would not have everything that we do. So off my soapbox, but it's really a lovely thing to show how this digging into deep, fundamental, not understood, mysterious things can 100 or 200 years later transform the world. And the type of science I do now, people often ask, well, what good is knowing about how the inside of atoms work, how the inside of quarks work? And I don't know the answer to that. But just being a little more pragmatic, if I go back, say, 100 years, where people were trying to understand how the protons and neutrons inside atoms held together, how they split, how you could combine them and so forth, this has led to nuclear power. Now, whatever you think about nuclear power, and some people like it and some people don't, but it is powerful. It will generate energy for humanity, and it may be that is the path that we take as we move away from digging fossil fuels out of the ground. Humanity is going to need power, no matter what. Nobody is going to go back to the way things were in the 1700s. And one enormous source of energy that is there for us to take, if we so choose, is the modification of the nucleus of atoms. Seem to have absolutely nothing to do with anything, and yet it provides humanity with an opportunity, which of course requires that we think carefully of how we do that, and if we want to, but it gives us something that we didn't have before.
Yeah, it's very clear that nuclear fusion and nuclear fission will unlock a huge amount of energy that's required for a civilization to flourish, but that's almost like near term.
Mhm.
Longer term, you can think about things like we'll talk about dark energy
Yeah.
crisis and antimatter. Maybe if you figure out some of the mysteries around antimatter, that too would lead to energy sources, how to produce energy. That too might lead to counterintuitive propulsion systems
Mhm.
for us humans to travel through the universe. Now, right now, it seems far-fetched, too expensive, too complicated, too difficult, but breakthroughs in the fundamental theoretical physics might lead us to unlock some incredible energy sources, incredible technologies that will allow humans to explore the universe. And of course, we should also mention that, as always with technology, it's a double-edged sword. It will most likely lead to the development of more dangerous weapons or
Sure.
other sources of harm. And then we, as a civilization, kind of have to walk that line and hope we figure out how to do more good than bad with the technologies we build.
Right. But we have to really remember, while people worry about nuclear weapons, which are admittedly very dangerous, and even nuclear power, which has waste that has to be dealt with, what science is doing is working out, finding power that nature has presented to us. This is not new. Fire is like that too. Fire can burn down your house or it can cook your steak. Power is like that. And that's just something that we have to understand as humanity. And that's why this needs to be when we talk about science, it has to be a broad conversation by all of society, because what scientists can do is figure out how the world works. Society has to figure out how we wish to apply that or not apply that.
Also, solving the mysteries and the puzzles of the universe in itself is effing awesome.
It is. It is.
So, I mean, that's the thing that makes us human in part, is looking at a thing and saying, how does this work? And then
Sure.
together, a bunch of apes get together, like poke the thing, kind of shake the thing.
Yeah,
And
yeah.
then over time, you have rockets going out into space. You build roads and bridges. You build the internet.